This week we're going to use what we know about the mean and standard deviation and that normal distribution to learn how to standardize scores, put them all on the same scale, make them comparable. We'll learn how to compute and use z-scores. So here's the situation. We need to measure all sorts of variables for all sorts of reasons. And we have a problem. We measure those variables on different scales, and therefore we can't compare values or even keep track of the meanings of the different values. All of these scores have different means and standard deviations, and the scores are not comparable. And how do we get these cutoffs anyway? If you look at the scale on the bottom of the distributions, you can see that in the top group of distributions, mu and sigma are both changing. Both are getting bigger as you move from the distribution on the left to the one on the right. Changes in mu just move the distribution to the right or to the left if the mean is getting larger or smaller. Changes in sigma expand and contract the distribution. And here's another way to look at it. And another. All those variables have different means and standard deviations. In order to understand them, compare them, we have to be able to put them all on one scale to standardize them. It might be meaningful to have the mean equal to 0 on that new scale, so that we knew by seeing a negative sign that the score was below the mean, and seeing a positive number we would know that the score was above the mean. It also might be helpful if the standard deviation of these new scores was 1, with that 1 meaning in our case that the score was 1 of whatever standard deviation the scores had before above the mean. Remember these scores? Ages of inauguration of all the U.S. presidents. We already have found the mean of 55 and the standard deviation of 6.52 for these scores. And now we want to transform the scores and put them onto a scale that all scores can use and that can be meaningful. We want a mean of 0 and a standard deviation of 1 for these new scores. We only have these options for the transformation. These options allow us to make linear transformations. They don't change the distribution shape when they are applied. Things like squaring or square rooting would change the scores as well, but also the shape of the distribution. Adding, subtracting, multiplying, and dividing by a constant will change the mean and standard deviation, but not the distribution shape. Remember that what we're going for is a transformation that will replace our mean of 55 with a mean of 0, so that positive scores are above the mean, negative scores are below the mean, and our standard deviation of 6.52 with a standard deviation of 1. So what do we have to do to move this distribution over to where the mean is equal to 0? We subtract a mean from each score. So we subtract a constant from each score, and that constant we subtract is the mean. And when we subtract the constant, that mean from each score, the new distribution will have a mean of 0. When we subtract the population mean from a group of scores, the new mean of the new group of scores is equal to 0, but the standard deviation is not changed at all by adding and subtracting a constant. Here are the original scores and the result of the transformation so far. You can tell that mu is going to have to change because the scores that previously ranged from 42 to 70 now range from -13 to 15. We can tell that sigma hasn't changed because the range 70 minus 42 equals 28 is the same for the new scores. 15 minus a negative 13 is 28 still. So the variability of the scores is the same. But we are halfway there. So let's get going with the other half of the problem. We need to transform the standard deviation of 6.52 into a standard deviation of 1. A transformation that turns any number to 1 is division by that number. So those mean differences divided by 6.52, our original sigma, will turn the standard deviation to 1. So now we have the transformation that will produce z-scores with a mean of 0 and a standard deviation of 1. Subtract the mean from each score, that gives us a mean of 0 for the z-scores, and divide that difference by the standard deviation. That gives us a standard deviation of 1. Let's do it then. So George Washington's age at inauguration was 57. Subtract the mean, so 57 minus 55, and divide by sigma. So 57 minus 55 divided by 6.51, and that equals 0.31. George Washington's age is 0.31 standard deviations, about a third of a standard deviation away from the mean. It's a positive number, so he was older than the mean, older than 55 at the time of his inauguration. Here's the z-score formula, and any score can be changed into a z-score. Systolic and diastolic blood pressure are changed here into z-scores. Both systolic and diastolic blood pressure in this graph are 2 standard deviations above the mean. Although they are measured on different scales, when we transform them to z-scores, they're located at the same place on the normal distribution. Both are high scores. So high, in fact, that we categorize those blood pressures as hypertension stage 2. So people who have a z-score of 2 for systolic and diastolic blood pressure are categorized as having hypertension stage 2. An ACT score of 31 is a very high score. It also is 2 standard deviations above the mean, and the z-score, therefore, is equal to 2. An IQ score of 100, on the other hand, is an average IQ score. So here we have someone with high achievement, but an average IQ. Some folks might call that person an overachiever. We can only see that when we put these scores on the same scale. And when scores are in z-score form, we can always get back to the original score. In fact, with 3 of the 4 values, we can always find the remaining value. So here, in this equation, we're solving for x. And here, we are solving for mu. Here we're solving for sigma. And we'll do more of that later, because now we need to know what else we can do with these z-scores. Here's what we know about the normal distribution. The mean is in the center of the distribution, as are the median and the mode. And the normal distribution is symmetric about the mean. That implies that half of the scores are above the mean, and the other half are below the mean. We also know that for a z-score, let's say a z-score of 1, the distribution is now divided into a body portion, the larger portion of the distribution, the part with more than half the scores, and a tail portion, the smaller portion of the distribution, the part with fewer than half the scores. And we know that the tail can be on either side of the distribution. It is always, however, the smallest portion of the distribution, and the body is always the largest portion of the distribution. So George Washington's z-score for his age of inauguration was 0.31, and that's a positive value because he was 57 when inaugurated, older than the mean of 55. We got that by subtracting 55 from 57 and dividing by the standard deviation 6.52. So if we start at the z-score, 0.31, the tail of the distribution is to the right. That is also the area above the z-score. with scores greater than 0.31. And to the left is the area below Z with scores less than 0.31. To the left is the body. The body is always larger and the tail is always the smaller part of the distribution. So if we want to know what percentage of presidents are younger than George Washington at inauguration, then we're asking about the body, the percent below Z. If we want to know what percentage of presidents are older than George Washington, then we're talking about the percentage of scores in the tail, the percentage of ages in the tail. The areas in the body and the tail are some proportion of the distribution that we can find and then multiply by 100 to get the percentage of the distribution in both those areas. James Polk was 49 years old at his inauguration, and his Z-score is minus 0.92. He has a negative Z-score because he was younger than the mean of 55 years at inauguration. If we want to know what percentage of presidents were older than Polk but younger than Washington, then we're talking about the area between two Z-scores, between Polk and Washington. If we want to know about ages of inauguration that are older than Washington or younger than Polk, we're talking about the area beyond two Z-scores, and we add those areas together. So we have all these ages of inauguration, and we have computed their Z-scores. And now we need to know what percentages of scores are below Z, above Z, between two Z-scores, and beyond two Z-scores. We're going to practice. So all we have to do is integrate the area under the normal curve to figure out those proportions. Just kidding. I told you that we wouldn't be doing hard math. Really, we don't need to worry about that calculus because we have a table with the proportions at each Z-score already figured out for us. Down the left column under Z, we have the whole number and 1 decimal of the Z-score. So if our Z-score is 1.07, then the 1.0 will be in the left-hand column. Across the top row, we have the second decimal of the Z-score. So if our Z-score is 1.07 and the 1.0 is in the column to the left, the 7 or 0.07 added to that 1.0 will be across the top. This Z-table always has the proportion in the body. If the Z-score is positive, the proportion in the body is the area below Z. If the Z-score is negative, however, the proportion in the body is the area above Z. The proportion has to be positive. Just think about it. It is the area under the curve, the proportion of scores in a section of a distribution. It can't be negative. When we take the proportion and multiply by 100, or just move the decimal over 2 to the right, we get a percentage. So for a Z-score of 1.07, we find the body of the distribution has 85.77% of the scores. We took the proportion 0.8577 and moved the decimal over 2 spaces or multiplied by 100 to get that 85.77%. For a Z-score of 1.07, a positive Z-score, the body is to the left of the Z-score. And so we found the area to the left of the Z-score or the area below Z. And we can start filling in this table. It looks like next we need to look for the area above Z. Well, because this distribution contains all the scores, 100% of the scores, if 85.77% are below a Z-score of 1.07, then 100 minus 85.77, so 14.23% must be above Z. And we can put that into the table. Looks like we need to find out what is between a negative Z-score of 1.07 and a positive Z-score of 1.07 next. What is between plus and minus 1.07? We already have all the information we need to find what's between a plus and minus 1.07. We know that 85.77% of the scores are below our Z-score of 1.07 and that 14.23% are above that z-score. And if 14.23% of the scores are above a z-score of 1.07, then 14.23% of the scores are also below a z-score of minus 1.07. The distribution is symmetric that way. So if 14.23% of scores are below a z-score of minus 1.07 and 14.23% are above a z-score of 1.07, then the rest of the distribution is between those two z-scores. We can compute that area as 100 minus 14.23 minus another 14.23, and that equals 71.54. Or we can just subtract the tail from the body, 85.77 minus 14.23, to get the between area. And we can put that in the between column of the table. To find the percentage of scores beyond two z-scores, plus and minus 1.07 for this problem, we just add the two tails. 14.23 plus 14.23 equals 28.46. And we put that into the table. So let's try again, except this z-score is negative. So the body is above z with a z-score of minus 1.38. We find from the table that 91.62% of the scores are above that z-score. And the table won't have plus and minuses on it because the z-score is symmetric about the middle. So whatever is true for the plus side is true for the minus side. And we put that 91.62 under the column for percent above z. From that information, we can compute the rest of the information. So we can compute the area below z as 100 minus 91.62%. So the area below z has 8.38% of the scores, and the area between z plus and minus z is 91.62 minus that 8.38%. So 83.24% of the scores are between plus and minus z-scores of 1.38, and the area beyond 1.38 and negative 1.38 is just adding the tail. We get from adding the tails. 8.38 plus 8.38 is 16.76. And we can put all of that into the table. Your job for your homework this week will be to fill in all of this information in this table. So yes, we have all these variables that we need to measure, and all these variables have different means and standard deviations. But we determined today that when we need a way to get all these different numbers onto the same scale for comparisons and just to be able to understand them, we have z-scores, mighty z-scores for that. So let's look at these variables again, this time through the lens of z-scores.